Hi guys, my name is Ellie. I'm going to attempt to tell you about NMR spectra when finding the molecular structure. So basically, NMR stands for nuclear magnetic resonance, and that instrument allows the molecular structure of a material to be analyzed by observing and measuring the interaction of nuclear spins when placed in a powerful magnetic field. So right now we're just going to look at ethanol. So this is the HNMR spectra for this structure. And what you would notice first, or at least what I would notice first, is that there's three different peaks. And so when we're drawing out the structure of ethanol, we can see that there's 1H, 2 implicit hydrogens here, and then 3 implicit hydrogens here. So those are the 3 different protons in our NMR because they all have different neighbors. So now that we know that there's 3 different protons, we are going to look at the position of those signals. So when we're looking at the spectral data, we can see what each peak indicates. So if we scroll down to here, this is the NMR table that will be given to you for any test. And so when we're looking at these peaks, we look at the x-axis. So this first one is in between 3.5 and 4. So go down to here, 3.5, 4. And so that would be our alcohol group because it's relatively short. And then when we're looking at our second, it's pretty much higher than that OH peak, and then right after 3.5. So that could say that's like somewhere around here. And then this one, very high, right after 1. So it would be our alkane group. And then once we know, so our list, we have an OH, we have a halide of some sort, or ester alcohol ether, and an alkane. So once we have those 3, we can look at the integration of the signals. So basically what that is, it's the area under the signal is proportional to the number of hydrogens to which the peak corresponds to. The integration function can also be used to determine the relative amounts of 2 or more compounds in a mixed sample. So it wasn't given to us here, but just for practice sake, I added here. So this peak has an integration of 1, this one of 2, and this one of 3. And as you can see, here's our OH. So here, I'll draw it again. Here's our OH, right? OH, OH. This CH2 would be here, and then this CH3 methyl group would be here. So another thing that I would look at is how many peaks there are. So when we're looking at, let's say, this 2H group, there is 1, 2, 3, 4 peaks. But when we use the n-1 rule, that would be 4 minus 1, which equals 3, which would mean it would have 3 neighbors. The CH2 tells us that it is a CH2, or you can also just draw it out. And then this would be unknown. This one would have, since it's 1 peak, 1 minus 1 is 0, so 0 neighbors. And this would just be, this is our OH. This one over here, 1, 2, 3. 3 minus 1 is 2 neighbors. Draw it out. And then this would be attached to something. So right now, this is what we have with our splitting pattern. In the molecule, the nucleus of an atom can induce in the electrons of the chemical bonds attached to it in a very weak magnetic moment. This affects the magnetic field at a neighboring atom's nucleus. So once we look at like what we have, so we have, and this one's a CH3 because of there are 3 hydrogens. So we have a CH3 that needs 2 neighbors and a CH2 that needs 3 neighbors. So that seems pretty logical that the CH2 would be attached to the CH3 because the CH3 would have 2 neighbors and the CH2 would have 3 neighbors. And so because the 1 hydrogen, 2 hydrogen are so close together, we would assume that attached to the CH2 group would be our alcohol. And by that, we can deduce the structure of ethanol. Yes, I don't think I needed that. Okay. And then, so next is ibuprofen, and just basically do the same thing. And so when we're looking at these different positions of, when looking at this table, and the different positions of signals, we can find the structure. So I will, okay, I'll draw the structure of ibuprofen here. Okay, so here is our structure. So when looking at our table, let's do this one first. So that's right at 11. Go to our table in 11. That's our carboxylic acid, which would be this group right here. It's not that, like this whole group. So I'll just label it. Okay, and then once we'll move down to these 2 peaks right here, right at 7.5 we would be looking at our aromatic compounds right there. That would be pretty indicative of a phenyl group. So that one would be this whole thing right there, aromatic compound. Oops. And then next we would do this one right here, which is right before 4, which would look like somewhere around here. So that one would be right here. And that would look like just a bond. And then the next one over would be right here. This one right here. I'll just color code it. This one, ooh, that's kind of hard to see. This one would be this bond right there, and then this last one would be right here.